Okay, this is PLC PID tuning, and I'm doing it for my instrumentation class. So that's where the ELC 213 comes in at. I want to start out with the model that I asked them to build, and this is basically what I asked them to build. And this is a step response or a change of input. This is your transfer function, which is every system that you control has some kind of transfer function. And you can spend a lot of time figuring out what that transfer function is. And then from that transfer function, you have the PID, which is where you can go in and tune and get different responses based on that. And that's what we've been talking about in our text. And then the PID would then go to the scope, and you would get to see the response. The feedback line, every time I change that one and save it and open it back up, it does weird stuff. So I'm leaving it. At least you can sort of see the flow here. So in my initial assignment, I said, here you go, use this transfer function, and the way to edit it is if I double click on the block, I've got a numerator and a denominator. So this is 1 divided by 1 over 2s plus s squared. So that is how I would enter it, and I can go in and change it. As you'll see, PID, initially we're looking for open loop responses, so your proportional should be 1, your integral should be 0, and your derivative should be 0. And I've set up the times so the simulation works, and I think that's what we did. And you basically go by defaults as much as you can. And there may be something that you changed, and I forgot what I asked them to change, but I changed it. So now if I hit the little run button up here, or the play button, a window opens and I see the system response. Now the green line is your set point, and the black line is your system response. So what we do is we need to come up with the slope of the steepest part of this curve. That is our R. We need to come up with our L, which would be this slope projected down to the x-axis, and the time between the step change and where that slope crosses the x-axis is your delay time. So in this case, our delay time is probably around 0.35 seconds, somewhere in that neighborhood. It's not very much. And then our slope is rise over run. So if I look at this part, I'm at 0.2 at this point, and you can zoom in. So let's do that. Let's zoom in. Let's see, there's the zoom window. Now, I did not zoom very well. So will it let me do it again? No. Okay, I'm going to zoom back out to extents, and then original. Let's go to that. Okay, now I want to zoom again. The other night I couldn't get it to do anything. Escape. That's fine. Let's just look at that. There we go. So now what I've done is I've changed it a little bit. How do I get out of zoom? Probably that. What's that do for me? Nothing. I'm going to rerun it. There we go. Okay, so you can always close your window, rerun it, get it back. Opens up a new window. This one opened, and we'll close that one also. So I need the slope of the line, the delay, and then my step change. Well, I was at 1 and I went to 1.5. So that was a 50% change. So I need my delta M, my delay, and my slope. And that's just guesswork. So I know my delay is 50%. I'm going to say my delay is about 0.35, and then I'm going to say my rise over run here is, let's do 1.5 seconds down to about a half a second. And what do I change? I change from about 0.6 to, excuse me, 0.1 to about 0.6. So it'd be a 0.48 over 1. Okay, so that gives me a 0.48 over 1. So let's go down to the bottom. What did we say our delay was? So I'm going to edit this document. So our step time was 50%. Our R is 0.48 over 1, or 0.48. And our delay time was like 0.35. Okay, so that's going to give me tuning constants, if you will. If I want to do P and I, which is what I recommend you probably do, you've got to come up with that delta, which we did, your R and your T. Okay, so then you take your R and your L and your delta and you multiply them. So 0.9 times 0.48 divided by R times L. So, calculate. Okay, bring up your calculator. Alright. 0.9 times 0.48 divided by, oops, 0.9 times 50. I'm not using the M. Okay, now it's divided by 0.48 times, and L in this case was 0.35. And what do I get? I get a 268. So that would be my P value. This is a different example. And then 3.33 times 0.35 is my I value. So P is 268 and I is 1.16. Okay. So those then go in the PID block. So I need my proportional to be 268. And this is just an estimate. It's just an estimate, so don't get too caught up in making perfect graphs. There we go. Don't get too caught up in that, because we're looking for a system response, and this is Nichols-Ziegler gives you a certain response, and it may not be the response you want, but it's a good starting point. So I'm going to click OK. Now what I like to do is always close this box, but remember what it looks like. Remember, our set point and our process variable never match, and that's what happens with proportional. So it should change, and so there you go. Now what you see is that my process does actually get to my set point because of my PID, and I've changed those values. And it looks like my proportional is a little bit high because I got a lot of overshoot, and you often don't want your process to do that, so maybe my calculation wasn't the best. I changed it in the wrong place. So this is another reason. So let's half it. It'd be 135, right? Okay. And then run it. It got worse. I guess I'm gonna come on down with the gain. Guess I need to go down by 10. So let's go down to 26. Give it a lot less gain. See, it just gives you a starting point. It doesn't necessarily give you the be-all end-all tunings. Okay, so here I've got overshoots getting better, but I'm still a little bit low. So this tells me I should probably increase my integral. So let's make that about a 3. And we'll come on down with this a little bit. Let's go down to about 18 or 15. Let's try that. And so now I'm getting there. I still got a little more overshoot than I want. Usually you want Nichols-Ziegler promises 25% overshoot. So what is 25% of 1.5? And then it settles in 2 or 3 cycles. So I'm still probably off a little bit, but you get the idea. So what I'm looking for, what I was trying to get on the worksheet, was give you a worksheet. Now give you a response. So I made this Word document, so you have a sort of what I wanted to see turned in, and I changed it. Instead of 1 times 2, I made it 1 times 10. And when I did that and I ran it, this was the open loop response. And so I came up with my R. The steepest part of the curve is hard to find. It's probably closer down here to the beginning, because you see it's flattening out as it goes up. My L, again, it's a guess of where the steepest part of the curve, if it came back to the line, where it would intersect in time. And my delta was 50. I made that one pretty easy. So whatever your open loop response is, you do delta, R, and L. And you can zoom in, just come up with numbers. Okay. And then for your P and I, these equations came out of the text material. For P and I tuning, P is for open loop, that, and your I is that, time I. Put those values back in your PID just like I did, and this is the result. It oscillates and then settles very quickly. So my question is, do you see the difference? Here's your open loop. Your process never gets to your set point, and then when you adjust your PID, and all you're doing is putting numbers in it, it changes. And so PID control gives us a chance to control the control a process. So now I say try closed loop. With closed loop, what you want to do is turn your I back off and then increase your P until you see oscillations that never settle. If you get a lot of oscillations but they settle, keep increasing your P until they don't settle. And then when they don't settle, you have something called your ultimate gain. And for P and I, your KP is going to be about half your ultimate gain. So for this one, I went in and changed it. This is what I came up with. And those became my P and my I values. Tuning it that way. And then this is my response based on the tuning. This is not really a great response because it never settles. Nichols-Ziegler should settle in 2 or 3 cycles. I forgot what it's officially, but it's only a couple. You should get an overshoot and then real quick settling to 0. So that tells me that my gain was probably too high. So I reduced my factor of gain by 10. I reduced my gain by a factor of 10. And I got this response. Which tells me that, hey, that's tuned pretty well because the green and the black line are the same. So that was what I was after. A open loop tuning, or seeing open loop response, tuning it open loop, tuning it closed loop. Want you to at least do one each way, and then you'll probably settle on a favorite. My favorite's probably open loop, but incidentally, when controllers auto tune, they do something that is like this closed loop. They're looking for oscillations in the process, and since they're mathematically doing it, they don't have to see a lot of data to see what happens. They can see how the graph's going in real time, so they can tune very quickly. They don't need to see 11 seconds of something. They can look at it very quickly in time to see what it's doing, and then they can ultimately they figure out the P and the I values based on what they come up with. If you can't remember how to figure the period of something, remember it's the time from one peak to the next. That's the period. And I did zoom in to get that of 1.2. Oh, 0.8, sorry, it's 0.8 seconds. So that would be the distance between that peak and that peak. And it doesn't matter which one you zoom in on, because again, it's just a starting point. Don't get too concerned with it. And in order to wrap this up, any system you ever try and control will have a transfer function, and you can spend a lot of time or little time finding out what the transfer function of that system is. Your PID control can either be in a PLC, it can be a standalone controller, whatever, but you're taking the signal from that physical system, which has a transfer function, you're controlling it, and then you're sending it back to it. And then we're just seeing the output. And that's how PID tuning works. It's really kind of neat in terms of what you're able to change just by multiplying and dividing. And you saw the PID equation because I had you put it in a worksheet. So that's all you're doing. You are taking numbers literally and controlling a real world system. And that's what PID does. And this exercise and the next one was an exercise in doing some tunings. For the second one, it's going to have you change the transfer function. Instead of 1 over, we were going to use 144 as the numerator and 144 here, and that would make this a 12. So that'd be like 120s plus s squared. And all it means is you'll get a different system response when you run it. So if I go in here and I change this, and this is the one I put on the worksheet for no special reason other than I thought it would tune pretty well. 120. So I've changed it. I need to get rid of my integral, put it back to 0, put the proportional back to 1, and if I run it, there is my open loop response. So from that, can I come up with delay? can I come up with slope? This one looks like it's got almost no delay. So if I come up with slope, use a very small number for delay, then I can come up with values that would tune this transfer function. Same process I just did. And I was looking to have you do it 4 or 5 times, and that way it will stick with you longer than just doing it once. So do a couple of these and get into it, and thank you for watching.